So far, whenever I've described the dynamics of quantum systems to you, and they've all been quantum gates, I've always just told you the laws of motion of each gate by fiat. Just a set of equations for how the representative observables of the qubits are changed by passage through that particular gate. Now I'll go to the other extreme and show you the most general framework for quantum dynamics and tell you in principle which sets of such equations describe processes that occur in nature and which don't. Laws of motion are about how things change with time. But as I said in the first lecture, the notion of a system changing itself implies that some things about it are invariant. That's what I called the constitution of the system. The laws of motion, the dynamics, are part of the constitution. The other part is the algebra of the observables at any one time, which in a system of n qubits is always the same as the algebra of all Hermitian matrices of dimension 2 to the n. So, for instance, you'll recall that this Pauli algebra is one way of summarizing the algebra of 2 by 2 Hermitian matrices, representing the observables of a single qubit at any given time. Now, since the algebra is invariant, the laws of motion have to be such that even though the observables change, their algebra does not. And that's obviously a constraint on what the laws of motion can be. For instance, take this equation for the commutator of the observables x and y of a qubit. Rearrange it, and you get a quantity which the laws of motion have to prohibit from ever changing at all. It has to stay fixed at 0 for all time. Differentiate it with respect to time. That too has to be 0. So there we have a relationship between the time derivatives of observables. And we know that this relationship must be not just compatible but deducible from the law of motion of any qubit that exists anywhere in nature. And we can get similar constraints from any other equation holding among the observables at any given time. It may sound as though it's going to be tricky to find any law of motion that enforces all of these intricate constraints on how observables can change with time. But no, it's easy to find one. Here's one. Pick any observable h of a quantum system at a given time. If the system is a qubit, then like all observables, h can be expressed as a linear combination with real coefficients of the representative observables x, y, and z at that time, and the unit observable. Do the same for every other time. In other words, pick a whole one-parameter family of observables, h subscript t, one for each time. The reason why I'm not calling that h of t with the t in parentheses is that we're already using that notation to refer to the time evolution of a single observable, whereas in this construction we're allowed to choose a different observable at each time. Now, given that one-parameter family of observables, consider the following law of motion. For each observable a of t of the system, dA by dt equals I times the commutator of h at t with a of t. We can express that law in a form that's more like the specific laws of motion I've told you in previous lectures by just integrating it over an infinitesimal period dt. So we get a of t plus dt equals a of t plus I dt times the commutator of h with a. And in that form, it expresses each observable at one time, t plus dt, in terms of observables at another time, t. H at t is, by construction, some observable at time t, and so is a of t. For gates, we were only interested in the relationship between observables before and after the gate acted. So we used laws of motion referring to a unit time instead of an infinitesimal time. Such laws could be obtained by integrating this differential equation of motion between t and t plus 1. Okay, now does our new law of motion preserve all the algebraic relationships that may exist between observables? Well, consider any such relationship at time t. We can always write it in the form f of a of t, b of t, and so on, equals 0, where a and b and so on are observables at time t, and the function f uses any of the operations of matrix algebra, namely matrix addition, matrix multiplication, and multiplication by a constant. It's sufficient to prove that f itself obeys the law of motion. Well, what can f be? Suppose f is a real multiple of something that does obey the law of motion. Then f obeys it too. Suppose f is the sum of two things that each obey the law of motion. Then again, f also obeys it. What if f is the matrix product of two things that obey the law of motion? Well, then d by dt of pq equals d by dt of p times q plus p dq by dt. And since p and q obey the laws of motion, multiply that out and you'll see that it's I times the commutator of h with the product pq, which is I times the commutator of h with f again. So the upshot is, however f is composed out of observables obeying our equation of motion, f obeys it too.